I'm Almighty God. I'm Master Sankoshi, and today I want to talk about chemical reaction engineering module in Capsule Multiphysics simulation software. Now I want to go through the chapter of theory for the vapor-liquid equilibrium interfaces. The following sections describe theory applicable for the vapor-liquid equilibrium interfaces: vapor-liquid equilibrium, evaporation and condensation, reference for the vapor-liquid equilibrium interfaces. Now I want to go through the vapor-liquid equilibrium. For a vapor and liquid system, thermodynamic equilibrium is reached when the fugacitities are the equal in both phases for each species I as follow. Here Fi to the power of V denotes the vapor phase fugacity, and Fi to the power of L is the liquid phase fugacity. The fugacity is a measure of the chemical potential and relates to the tendency of a substance to prefer one of the phases over the other. In general, the fugacity in each phase depends on the temperature T and absolute pressure P as well as the composition. The composition is usually expressed by the molar fractions in the each phase, such as YI and XI respectively. When accounting for the non-ideal behavior, the fugacity equality in question 3-191 can be formulated as follows. Here the fugacity coefficient Phi prime accounts for non-ideality in the gas, while the activity coefficient gamma I accounts for the non-ideality in the liquid phase. Both these coefficients are functions of temperature, pressure, and fraction of species I in the respective solutions. For the liquid, Phi saturation and Pi saturation denote the fugacity coefficient and the vapor pressure. Both for a pure species are the subscript sat or saturation indicates saturation conditions. The exponential term on the right hand side is the pointing correction factor, including the molar liquid volume Vi to the power of L is equal to Mi divided by rho to the power of L. Here Mi is the molar mass of a species I and rho L is the liquid density. The correction factor describes the effect of pressure on the liquid fugacity for lab pressures. The pointing correction factor is close to 1 and two simplified relations can be formulated. In the case of an ideal gas mixture and an ideal liquid solution, the fugacity coefficient and the activity coefficient are both 1. Equation 3-192 reduces the Rowlett's law, such as blue formulation for an ideal gas mixture but a non-ideal liquid solution. Equation 3-192 reduces the modifier Rowlett's law, assuming that the thermodynamic equilibrium prevails at the vapor-liquid interface. The molar fraction to be described on the vapor side of the interface is in general from equation 3-192. The vapor-liquid solution interface feature uses separate composition variables for the two phases along the droplet surface to enforce a thermodynamic equilibrium. The composition on the vapor side is prescribed from the equation 3-195 using the liquid composition, the temperature and the pressure at the surface when the feature is coupled to a thermodynamic system functions for both the liquid phase fugacity and the vapor phase fugacity are available. It is possible to prescribe a vapor pressure for each species. In this case, the system is assumed ideal and the vapor molar fraction is as follows. The vapor-liquid interface uses the same formulation for the vapor-liquid equilibrium, but the composition in the liquid phase is user specified. It can be used to model vapor transport to or from a liquid where the composition changes are assumed small. The transport of concentrated species in vapor interface solves for the mass fractions denote omega for species are the boundary condition applied on the vapor side of droplet surface is as follows, where Man to the power of V is the mean molar mass of the vapor using the ideal gas law of the form such as follow. The vapor side concentration corresponds to blue formulation. Now I want to go to the evaporation and condensation. Vapor-liquid equilibrium is enforced by prescribing the mass fractions in accordance with equation 3-195. The resulting vapor pressure derives evaporation and condensation across the vapor-liquid interface. When the vapor pressure at the interface is higher than the ambient vapor pressure, mass evaporates from the liquid into the vapor. If instead the vapor pressure drops below the ambient vapor pressure, for example, due to decrease the temperature, vapor will instead condense into liquid. The processes will proceed until the vapor pressure at the interface and the ambient vapor pressure are in equilibrium. The total mass flux transported across interface based on the SI units kilogram per square meter second can be computed by summing all fluxes of evaporated species in the manner of equation 3-200. Here, GI to the power of V denotes the diffusive mass flux resulting from the enforcing the equilibrium conditions in equation 3-195. N is the surface normal and U to the power of V, the mass average of vapor velocity at the interface fluxes from a species that doesn't evaporate or condensate should not be included in the sum. Assuming that the interface is stationary, the total mass flux is used to define a step-on velocity to be applied at the interface, such as 3-201. For two-phase fluid, the relationship governing the velocities of the vapor and the liquid at the surface is as follows, where the mass transfer across the interface corresponds to the total mass flux Jr to the power of v, it can be denoted that a non-zero mass flux is necessary for the phase velocities to differ. The difference is prescribed in the normal direction of the surface. For two-phase flow with evaporation, the position of the vapor-liquid interface needs to also be updated. When using a moving mesh to track the interface position, the relationship between the mesh velocity and liquid velocity is as follows. The mesh velocity is the velocity of the vapor-liquid interface in a situation without evaporation or condensation. The normal mesh velocity equals the normal liquid velocity, which in turn is equal to vapor velocity according to equation 3-202. For a non-zero mass flux, on the other hand, the interface normal mesh velocity differs from that of the liquid phase. To conserve mass during phase transfer, the normal mass flux on the liquid side should equal that of the vapor side. The normal diffusive mass fluxes on the liquid side are therefore defined as follows. The heat of evaporation at the vapor liquid interface is based on the SI unit is watt per square meter is defined as follows. Where delta H vaporization I is the species heat of evaporation based on SI unit is joule per kilogram when cooled to a thermodynamic system, functions for the heat of evaporation are added automatically. I read a literature that was written by Pauling. The name is Connell. The Properties of Gases and Liquids, the fifth edition. Now I want to go through the theory for the reacting laminar flow interface. The following sections describe theory applicable for the reacting flow interface. We want to go through the pseudo-time stepping for mass transport, the Stefan velocity, the chemical reaction rate, non-isothermal reacting flow, and references for the reacting flow interfaces. Now I want to go through the pseudo-time stepping for mass transport. In order to improve solution robustness, pseudo-time stepping can be used for the transport of concentrated species interface when solving a stationary model using pseudo-time stepping, a fictitious time derivative term such as follow rho omega I minus no jack omega I divided by delta T is added to the left hand side of the mass fraction equations. Here rho is the fluid mixture density, omega I is the mass fraction dimensionless of a species I, and delta T is the pseudo-time step. Since omega I minus no jack omega I is always zero, this term doesn't affect the final solution. It does, however, affect the discrete equation system and effectively transforms a nonlinear iteration into a time step of delta size of delta t prime. For a description of the pseudo time step term for the Navier-Stokes equations and the pseudo time step, see pseudo time stepping for laminar flow models and pseudo time stepping in the COMSOL Multiphysics Reference Manual. Thank you so much for watching my tutorial video until the end. Today is 20th of May 2026, time is 11:52 a.m. Also, you can download the appropriate and proper COMSOL file simulation from my github.com/master script.